Okay, so tonight's meeting, the first part is going to be Nolan VE4NOL, who will be doing a presentation on multimeters. And I just need to find it and share the screen. Start with that one. Share. And slideshow start.
You won't be able to share the slideshow.
Yes, you can.
Oh, cool.
That won't be.
I'll treat your legs tomorrow.
All right.
Oh, cool. Click onto that. Your thumbs, guys.
All right. Again, I'm Nolan, VE4NOL, and just gonna go quickly over a few things here about multimeters. So I'm not gonna kill you or bore you with all the math, but there's a few calculations I've got down and some schematic diagrams, just to more see what's going on inside the meter and the individual parts of it, and just that it's there. Just to give us a better idea of what we're actually looking at and what we're doing when we're taking measurements. So I'm pretty sure most of us in this room have used a multimeter before. So we're just going to dive in a little bit deep what's actually happening kind of behind the scenes. So a couple of key points we'll go through. We're going to look at DC voltmeters, DC ammeters. And I'm going to start off, everything's going to be based off of analog meters. And then we'll talk a little bit more about digital. So DC voltmeters, DC ammeters, ohm meters, using a DC meter to read AC values and accuracy of measurements. We'll put that to the back.
I don't know what that is.
It's the Zoom, I guess.
I can't get rid of it. Sorry.
That's what Zoom is sharing. So they're only seeing like half the screen.
Oh,
Really? Can you hit escape for a second?
okay.
Which Zoom? I'll show you start with
No phone. There's no presentation.
Try this again. Share. That screen. Share. It's gonna do the same thing, it's got that border on it. You're only seeing part of the screen, yeah?
F5.
Yeah. You've done it before, I don't understand.
I click
Hit
on the
escape
green
again.
box. Okay. Here, but you can see the full screen now.
No, perfect.
Okay,
There we go. Thank you.
Yeah. So
thank you.
Look at
That's why you got 95% in your exam.
that. All right. Okay. Just a couple of quick fundamental formulas that I'm just going to breeze over. I'm going to be making reference to. We all know these, so they would have been on your exams. So parallel resistance, right? Obviously, 1 over RT equals 1 over R1 plus 1 over R2. Series resistors is just total resistance is just an additive of all the resistance in the circuit. Ohm's law, V over IR. Kirchhoff's voltage divider laws, right? Your source voltage minus the voltage drops through your circuit are going to equal to 0. And Kirchhoff's current divider laws, which is basically just the currents added up together minus from the total current is going to be 0 as well. So basically Kirchhoff's law is just current entering equals current exiting. All right. So DC current meters, rules of measurement. Current meter must always be connected in series with the load. There are never any exceptions for this. Failure to observe this rule can result in permanent damage to your instruments. Use a meter with a full scale current rating greater than the maximum current expected in the circuit under test. Use a meter with an internal resistance that is low in comparison to the resistance of the circuit that is under test. And if measuring current in large complex circuits, always connect a meter in a branch circuit that's under test. A DC current meter as an ammeter. So just a couple of, I just jotted down from what I'm going to be putting up on my schematics here, just basic descriptions of what some of these values are. So VS is your open circuit voltage. RM is the internal meter resistance. IM will be the current through your meter in amps. RS is going to be your source resistance, i.e. Battery's internal resistance, and then R will be your load resistance. So current flowing through a meter is always going to be equal to IM is VS minus the additive of your resistances. So your load resistance, your meter resistance, and your source resistance. Being that your meter resistance and your source resistance, the resistance of a battery is usually fairly low. We don't really regard that. So we basically just look at it as meter resistance is going to be your source voltage divided by your resistance of your circuit, right? And just a basic Ohm's law to prove that. So again, I'm not going to kill everybody with Ohm's law here. So obtaining a higher scale, obtaining higher current scales. So a higher current scale can be achieved by adding a shunt resistor or low resistance in parallel with the meter. If the shunt resistor is lower than the meter resistance, then the majority of the current will flow through the shunt resistor. So essentially, as you see in our diagram here, we have our meter, which shows full scale deflection is around 100 microamps. If we were to measuring current through the circuit, we see we have a load resistance of 10 ohms and a source voltage of 10 volts. So Ohm's law will tell us that we have 1 amp flowing through that circuit. And because it's a series circuit, we know that if we have 1 amp flowing through the circuit, we have 1 amp flowing through our meter. But our meter can only handle 100 microamps for a full scale deflection. So we would have to put a shunt resistor, which is just a parallel resistance in there. Right? So basically, we can have 1 microamp flowing through our meter and 0.9999 amps flowing through our shunt resistor. So we can calculate out that shunt resistance. I've put the math up there for you if you want to go through it, but yeah, basically just Ohm's law. So it works out that our shunt resistor is going to be 0.05 ohms. Right, so the majority of the current goes through a shunt resistor. So this is why our meter has to be in series with our circuit, and why we use a shunt resistor, right? Because the actual meter itself can't handle those high currents. So we can add multiple options for shunt resistors in there. So by changing those, we can actually adding different options. We can change the scale on there. So a lot of the older meters, got an example of one here. Probably the people online can't see it, but you often have a selector switch to select your scale. So that's all you're doing is literally just selecting a different shunt resistor. Right? So by using a selector switch and a combination of shunt resistors, we can provide multiple ranges of currents to select from. It's always important to select a scale higher than what your expected current is, so you don't burn out your meter. And for accuracy, you want to keep that scale as close to what you're actually reading as possible. So usually start out a little higher and work your way lower. And for example, you wouldn't want to use the 10 amp scale to measure a reading of 121 microamps, right? Because you're not going to see any deflection on your meter. But again, realizing that your meter is part of that circuit, right? So your shunt resistor does actually look like a load resistor in that circuit. DC voltmeters, rules of measurement. So voltmeter must always be connected in parallel with the load. We use a meter with a full scale voltage rating greater than the maximum voltage expected in the circuit under test. We use a meter with an internal resistance that is high in comparison to the resistance of the circuit under test. And if measuring voltage in large complex circuits, always connect the meter in a branch circuit that is under test. Yeah. Same kind of idea. We have our meter there, and our source voltage is 10 volts. Our meter current is going to be 100 microamps with an internal resistance of 500 ohms. That's not going to work on this 10 volts, so we'll have to add a series resistor in series with the meter, right? So the series resistor is going to drop the majority of the voltage, allowing when we're going to calculate out for our full scale deflection of current we want coming through the meter. So our meter total resistance would be 10 volts divided by 100 microamps. So we know we need 100K of resistance between across our meter. And we know that our meter's internal resistance is 500 ohms. So to figure out what our series resistor would do, we just minus the 500 ohms from our meter's internal resistance, and that would give us 99.5K ohms resistor for our series resistor. So again, showing you this to see that how similar the circuits look. The meter actually looks like a circuit, right? So you can see it's got a series resistor. The meter itself, it's two resistors in series with each other, right? Which are in parallel with our load resistance. And then again, obviously we create more than one scale for accuracy by adding multiple options for series resistors. And again, always important to select a scale higher than what's expected. And for accuracy, try to get that as close to of the reading that you're actually reading. So I wanted to bring these up because when we look at this, we have to realize, let me go back for a second here.
It stopped. Screen sharing.
Well, how do I do that?
Share. No, green one.
So in this situation here, where we've got our shunt resistor, right? We have a total resistance here between our meter resistance and our shunt resistor, right? Those are parallel resistors. And we can calculate our total resistance there by using parallel resistor rules, right? And then that resistor is now in series with our load resistor. So we've actually changed the resistance of the circuit by adding the meter into it. So now it's actually going to change what our current flow is to that circuit. So our meter it's become part of our circuit. It is affecting the circuit that we've got under test, right? Same thing when we get into a voltmeter.
You want to record?
Yeah. You again. So we see the same thing on a voltmeter. We now have two series resistors, right, that add together, and they are in parallel with our load resistor. So this is no longer a total resistance of 10 ohms, right? It's actually going to be, the parallel of these two together. So we have, again, changed the resistance of our circuit by simply connecting our meter into it. So our meter does influence our circuit. Making sense?
Is that in addition to what the shunt resistor?
Right. Well, so in a shunt resistor, it's going to change the resistance because it's a series resistor, right? So it is going to add to the total resistance. Now, if your shunt resistor is 0.05 ohms, that's what you're increasing your resistance of your circuit by. So if it's, you're measuring a value that's currents flowing through a load that's maybe 10K ohms, that's not going to be a huge difference because now you're 10.0000.
What's the meter? But the meter itself, it doesn't add to the shunt resistor?
Yeah,
Oh,
for
yes,
sure.
okay.
Yeah, they work together. Yeah, it's a combination circuit, right? And then just like in here, we've got a voltmeter, right? We have our series resistor and our meter resistance are in parallel with our load resistance. So we know in parallel circuits, your total resistance is always less than your smallest resistor. So because we're using a higher resistance here, it's going to lower the resistance of
So how
this.
do you know what the meter is contributing?
Well, the meters will tell you that, like there'll be a data sheet on it when you
Oh,
get them. So in the case of voltmeters, you want a really, really high resistance to your voltmeter, right? The lower the resistance, the more it's going to influence the resistor that's in parallel with. Whereas in a current meter, you want the opposite. You want a really, really low shunt resistance because the higher that gets, the more it increases your circuit resistance. And the more it's going to reduce the actual current flow through your circuit.
A specification on.
It'll be a specification on the meter. Yeah. I just wanted to touch base on like those are basic how they're designed, so you can see that you are actually changing the circuit by just simply putting the meter into that circuit. So as soon as you touch your test leads in there, you've changed things. So you got to think about that when you're reading your measurements and how is that going to affect your accuracy of what you're reading, right? it is going to change it. Ohm meters. Rules of measurement. So never connect an ohm meter to an energized circuit. Fluke meters, they're a little bit more forgiving. They'll scream and beep and flash lights at you. But you know, a lot of the lesser expensive meters, you have it on ohm meter, set to ohms, and you put it into a live circuit. You're gonna probably let the smoke out of it. An ohm meter is connected across the component to be tested. If individual components are in a complex circuit to be tested, you must remove the component from the circuit. Right? Analog ohm meters have to be zero. So you remember anybody's used an old analog meter, you touch the leads together, you have to adjust the zero dial on here to zero your needle. Digital ones, you just turn them on. Just go to always make sure you're using a scale that's larger, but it's close to the value that's being read. And ohm meters can be used to measure continuity as well, right? So that's basically just a really low resistance reading. Be sure not to touch the test probes while you're testing your components. That's it. Because your fingers will have some, your body will have some natural resistance to it, and it will as well affect your measurements. And of course, battery, as the batteries age, that's partly why you have to zero the meters. And get to a point where your battery gets so low that you won't be able to zero the meter. So make sure that your meter does zero before making measurements, or you won't be able to trust the measurements that you're making. How does the series ohm meter work? So there are three types of ohm meters. There are series, parallel, and series parallel. We'll just briefly discuss on series and parallel. How do they work? Well, same thing. You have a meter. It's got an internal resistance. You're going to provide your own power source, and then you're going to have your zeroing resistor that's going to zero in your meter. And how do we calculate that? We just use our basic Ohm's law, right? So our resistance to be tested, we would essentially just superimpose it here without having to go through everything individually. But yeah, E times R divided by E minus your meter resistance plus your zeroing resistance is going to give you what your current flow is going to be through that. So series ohm meters do not work well with low resistances. They work really good at high resistances. But again, you can see that it's all becomes part of the circuit, right? So if you don't have this zero, you're not going to be able to get an accurate reading on your resistance on your test. Shunt or parallel ohm meters, same idea. Just to use a parallel resistance, or the load being the resistor being tested is going to be in parallel with your meter. So, but they have the same thing. You're going to have your zeroing pot on there to zero your meter. Again, I'm not going to kill you guys with all the math because we all know this Ohm's law stuff. So, okay, measuring AC, using a meter to measure AC. So, again, we talked about these meters are DC devices. So, how do we measure AC with that? Well, we have a couple of options. We can use, obviously, we use a rectifier. We use a half-wave rectifier, full-wave rectifier, or a bridge rectifier. So, obviously, half-wave rectifier is going to give us, what is that, 0.47 of, or average, or not the average, of 0.47, I think, of your total peak voltage. Whereas a bridge rectifier is going to give you, basically, it's going to give you the RMS of your peak voltage. So most meters you're going to see are going to have a full bridge rectifier in them. And a bridge rectifier, we noticed the 4 diodes. A bridge is that diamond shape. So as well with ohm meters, we can use a bridge circuit as well. We put our meter in between our bridge, and then one of the legs would actually be our resistor under test. But again, we're not gonna get too deep into that. Just remembering that it's part of our circuit. So I'm distracted here. All right, true RMS. So you will see this on meters when you buy them. They all say they are a true RMS meter. Just about every digital meter that you buy will say somewhere, usually around the top, that it's a true RMS meter. What does this mean? Well, again, we briefly touched on how we use different types of rectification for measuring AC values. So an AC meter is going to read either the average of the waveform, which is 0.3, well, 63.7% of the peak, or the peak of the sine wave, right? That's 0.63 is your average of your peak. True RMS meter is going to read the equivalent DC value of an AC waveform. Where I'll go with RMS. RMS is, so it's effective power. So an AC waveform, your DC value, because it's a straight solid output voltage and going through your load, you're going to have a power, like your watts, is going to be continuous, straight. In an AC form, because it's alternating, once you rectify that, you still have a rectification, but it's still an increase, decrease, right? Increase, decrease to your peak of your waveform. So because you have those values where you have no voltage in between or lower voltage, it's not going to be the same amount of power. So if you have, say, 10 volts DC and you want the equivalent in AC, you would have to have 14.4 volts to give you the same amount of power, effective power going through that circuit. You have to increase it by the square root of 2. That's basically RMS in a nutshell. So a true RMS meter is going to read the effective DC value of that AC waveform. So if you stick your meter in the plug at home and it says it's 120 volts, it's actually 100, and peak of that waveform is 174 volts. But it's giving you the RMS value, which is 120. So how do we do this? So a true RMS meter is going to read the equivalent DC value of an AC waveform, regardless of the shape, complexity, or any anomalies in that waveform. If we're talking about just straight AC, right? But often we're using these in radio circuits where you're going to have different complexities or anomalies that are happening within that circuit, right? The waveforms are changing because we don't listen to pure tones. We listen to voices which change. So the circuit is called an RMS to DC converter. It will produce a DC output voltage that is equivalent to the RMS value of the input waveform. These circuits used to be very complex and expensive, but with modern integrated circuits and software, they've become much more simple. Pretty much all your new meters today, this is all software based. It's, the program inside's doing the calculations and the work for you, as opposed to the old one meters like this, which has actually got vacuum tubes in it, where you can see physically a lot larger, and takes a little bit more to do that stuff. I'm not even sure if this one would even measure RMS.
It's like software-defined radio.
Yes, exactly.
Much more efficient.
Much more efficient. So how does the true RMS work and why? So the meter takes multiple samples of the waveform. Each sample value is squared. The square values are averaged. The square root of the average is taken and used to calculate out the true RMS. This provides accurate readings of both sinodal and non-sinodal waveforms and complex waveforms. So it'll give you RMS value. It doesn't matter if it's sine wave or if it's a triangle wave, sawtooth wave. As well as they can handle distortion caused by noise or harmonics, right? So then noise and harmonics aren't going to change it because you're taking an average. So that can be really helpful as well too in radio circuits. And the multimeter. Multimeter is just simply a combination of all these different meters put together into one convenient package. These are some of the common features that you'll see on multimeters. We've all looked at them, we've seen what they are. All right, analog versus digital. Why the difference? Why would you choose one over the other? So analog meters can monitor signal fluctuations in real time, right? So if things are changing and bouncing, that needle is going to be swinging and bouncing. So you can physically quickly see that those small changes in it. They're less susceptible to electrical noise or distortion. They do have lower resolution displays, right? And when you look on the display, you're only as accurate as your values on the display, right? The meter has to be zeroed. That's not zero. That's not going to give you a proper reading. Polarization range mode errors can cause damage to the equipment, and they're more susceptible to bumps and drops, right? They don't handle being banged and kicked and falling off ladders. Digital meters have internal resistance that naturally improve the accuracy. So an analog, again, like I was saying before, an analog an analog voltmeter is going to have a much higher resistance because you're putting that in parallel, which is going to give you a more accurate reading. And same thing with reading in current, where your ammeter is going to have a much lower resistance. So it's not going to affect your circuit as much. So it's going to give you much more accuracy. Obviously, they have easier to read displays with a higher resolution, meaning that they can give you a lot more zeros, so you can get a more accurate reading. There's no moving parts. They're auto ranging, so you usually don't have to set, what scale you're measuring on. They usually just the software does it for you, and it eliminates polarization and incorrect mode errors. So if you put an analog meter backwards an analog voltmeter backwards onto your battery, your needle is going to try to bury itself, and it can actually bend it. Whereas on a digital meter, it's just going to give you a negative reading. Right? So, and one of the other downfalls to it, digital meters is they do require batteries, and when the batteries die, that's it. Right? You're kind of dead in the water. Analog meters don't use
9-volt batteries, at least Blue does.
They're getting away from that. This one is 3 or 4 AA's.
What model is that one?
This is the 3000 FC.
Okay.
Yeah, true RMS right on top. So this one has Bluetooth on it, so I can connect it to my phone, or other meters like a clamp meter and stuff. I can connect them all together so I can see all my values on one display, which is kind of a nice feature to
I
have.
have a great idea how to maybe write a program to calculate a value for the true RMS, but I was really curious, how does the analog circuit do that? How does the analog circuit to do those complex calculations?
They would usually use comparators. So you would have an op-amp circuit that would take the take the values, and then you would use those to calculate it out. I don't really remember. That was years ago when I went through all this, but I do remember a big part of it being there being op-amps used to do that, and bridge circuits. So I'd have to look more deeply into that to answer that better, but yeah, they were a lot more complicated. Before that, I don't know what they did before that. Like a meter like this that uses tubes. Well, they're pretty genius people that come up with that. Accuracy display. So obviously you can see here, we've got 3 decimal places. So as accurate as that meter reads on the digital display, we got 3 decimals. If that meter can read that accurate, then it's going to give us a value to 3 decimal places. We look at the analog one here, and we look at, say, the AC/DC 12 amp scale. We can see it's marked out by 1 amp increments. So the most accurate we could read is somewhere halfway in between, say, a 1 and a 2, so 1.5. So 0.5 increments is the most accurate we could read on that particular scale, right? So digital voltmeters, their displays tend to give you a little bit more accurate readings than you can see on analog displays. And obviously from a glance, they're much easier to read and decipher. So less visual errors on that as well. So, okay, recap. So we talked about how DC voltmeters work and how to connect them to a circuit. We talked about how a DC ammeter works and how to connect into a circuit, right? DC voltmeters are in parallel, DC ammeters are in series. Talked briefly on how ohm meters work and how to make measurements, right? You have to take the component being tested out of the circuit, make sure that you zero your meter, how rectifiers could be used to measure AC values, and how accurate our measurements are. So key takeaways. So to kind of sum this up, the points I was trying to make here is it's important to remember that you are inserting your meter into the circuit and it becomes part of that circuit. Your meter will influence that circuit and change the circuit characteristics, right? You are adding resistance into a circuit, no matter what, even on analog or even on digital meters, whether it's a much higher or lower resistance, you're still adding resistance into your circuit and you're changing the circuit characteristics. And that along is one of the key things that will affect the accuracy of your readings, right? As well as displays and the quality of the meters. So yeah, just remember that when you use your meter to take the measurement, you are in fact changing the circuit just by measuring it. So, all right, questions? No, all right.
Anybody online have a question? Nothing here.
All right, there you go. Okay, anyway.
I actually have a question.
Yes.
If you were buying a meter,
Yes.
what meter would you buy?
Oof.
You still have analog meter in the market? Oh, yeah.
Yeah, oh yeah, you can still get analog meters. Yeah, they get really expensive. So I've had some Fluke meters. One of the things I like about Fluke is they come with a drop rating. This one's rated for 6 feet. A little bit higher quality ones will get you 10 feet. A meter like this, it's a kit. I've got the clamp meter with it. You're still looking at about $600. The thing I don't like about Fluke is they obsolete and delete their models about every 4 years to 5 years. So they say it has a 10-year warranty on it, but after 4 years, they don't carry the meter or the parts anymore. And they tell you got to replace it at your own expense, unless you can find somebody that will fix it. I've worked with Ideal meters. They're give you about the same accuracy of ratings as the Fluke does. They don't have as high of a drop rating, but they're about half the cost, right? Bought the cheap little Princess Auto meters, and you step on them and they break. Oh yeah, there we go. We've got a deal. Is that Ideal? Yeah, yeah, Ideal. So there's Ideal. Look very similar to the Flukes, and you can feel it. It's a pretty solid meter. Yeah. So, but the Princess Auto ones you're paying, $10 or $20 for, and you just go and buy another one. Exactly, right? It's like buying a Baofeng. So yeah, it really depends on what you're looking for. I use this one in areas with extremely high EMF, where you're in rooms with like electrical rooms with big transformers and stuff. It always seems to work. I've dropped this thing off my ladder more than 6 feet and it's bounced and not cracked yet. So but again, I've had my last but 3 meters ago I had where this selector switch actually broke and this thing would just turn and it wouldn't adjust. And I had to find a guy that would drill it and tap it and glue it, and Fluke basically told me I was on my own. So but yeah, I bought another one. So yeah, it really all depends on what you're looking for. So as far as it goes for the measurements they take, yeah, they're all pretty close. So
I have a question.
Mhm.
They call it overcurrent devices or overvoltage?
yeah. So that's the one thing I do like about this Fluke, and I did it today, not paying attention, had it on ohm reading, and I put 600 volts through it, and this thing started screaming, and the red light started blinking, and it was really upset. And I flipped it over to voltage, and then it was
Don't do that.
it was happy. Yeah. They do have fusing in them. This one is only rated for milliamps. 400 milliamp is the max you can measure on current with this, but like I said, I have a clamp meter that I typically use for current. So, but they do have fuses. They do have internal fuses inside. The fuses are stupid expensive. That 10 amp fuse from Fluke is about $50.
But
Yeah.
it's a really good fuse.
Yeah. Other things that catch on is I have a magnetic strap. Right, I can stick this on. I bought this off of Amazon, $25. The Fluke one locks into here. It's rubber. It's about this long, $80 for a magnet. So, there you
But
go.
it's a nice magnet.
It's a nice magnet. And it says Fluke on it. All right.
Anything else? Any other questions? Thank you, Nolan.
Very perfect. There you go. Yeah.
Can you turn off the projector, please? Green button twice. Thank you.
Must have made a lot of errors. Everything's almost all red.
Traditional way of teaching.
Ah, yeah, I'm gonna do the traditional way, yeah. Not the advanced technology way. Shall I just go?
Yep.
So if you remember, because I was hiding back in the corner, I said I'm Jeff VE4AE. I'm still Jeff VE4AE. And I noticed that in the website, they say I'm going to talk about satellites. I'm not talking about satellite. So somehow a communication occurred. I'm going to talk about a sudden ionospheric disturbance measurements. Okay. Some of you may have been the last time I spoke, which I spoke about a hydrogen radio telescope that I built. This is a device to measure the ionosphere. So it's not really a radio telescope, but it's close. And now I have to thank right up front two other people, or three other people that worked on this. One is Utra, VE4 UAV. She took her training here and got her basic with honors, and Brad Chase, VE4 BSc. And I'd like to thank Jim Sutton, VE4 SIG, because he needed some of the educational materials, which I'll be referring to later. Utra is not with us anymore, not because she's gone anywhere bad. She's gone off to Queens to take some courses. And her sister, which helped, Avia, I should have mentioned her, she's off to Oxford. So, we have trouble keeping these people. They disappear off for greater training opportunities. Hopefully they'll come back. So, SID. It's not a name. Sudden ionospheric disturbance. I'm going to talk about several things today. Actually, many things. I'm going to talk about the Earth. I'm going to talk about the atmosphere. I'm going to talk about the ionosphere. I'm going to talk about solar weather. I'm going to talk about CMEs and flares.
The one that happened today.
Yes.
Yeah.
I'm going to talk about the Carrington event. I'm going to talk about VLF, very low frequency transmissions. I'm going to talk about the D-ionosphere in VLF. We'll talk about Stanford Solar Center, Palo Alto, California. I'm going to talk about the actual SID monitor, which of course includes an antenna, an amplifier, A to D converter, and software in order to figure out what's going on. And then we'll talk about data analysis, and we should be out of here before the bars close. Which is what, 2 a.m.? I don't know. 2 a.m. Okay. So let's talk about the Earth. We all know what the Earth is, right? It's an oblate spheroid floating through space. It's about 12,000 kilometers in the belly and slightly less from the top to bottom. It's like me, wider. Yeah. We tend to get round. Oh, why am I looking at Garrett? Tend to get rounder as we get older, right? The Earth is like that. It's thicker around the middle because it spins, and during it, at least that's the model, right? During when it got made, it was spinning and got fatter. So that's where we live.
I believe none of us believe the Earth is flat. None of us.
None of us? Wait a minute, we'll check. Who's for Earth is flat? Because this whole talk will not make sense to you. Good point.
The universe is.
All the universe is.
Wait.
Yeah. Okay. Let's talk about the atmosphere. So, if the Earth is 12,000 kilometers across, how thick is the atmosphere? You guys must know this, right? Well, NASA says if you're above 80 kilometers, you're in space. because they got to get wings out, and that started with the X-15, right? The guys flew up 81 kilometers, and they said, "Oh, you're in space. We'll give you wings." The international associations say, "Well, the atmosphere goes up, and you're in outer space at 100 kilometers. It's called the Kármán line." So think about this for a minute, right? This is what, if you start thinking about this, it blows my mind. You've got a sphere 12,000 kilometers in diameter and an atmosphere that if I drew this, I couldn't draw the atmosphere. It's so thin, right? So thin, yet it protects us. This tiny, tiny amount of gas, most of which, by the way, is created by organic activity, like plants and animals. Oxygen. If you have a planet without life, you would have no oxygen. So this atmosphere, 20% of which was created by life, was incredibly thin. If it went away, other than the fact we couldn't breathe, we'd die. We'd die from radiation. We die from X-rays. We die from UV, right? We're not going to live out on the surface of Mars because Mars has no magnetosphere. It has no atmosphere to speak of. If we think ours is tenuous at only 100 kilometers, doesn't even exist on Mars.
Musk want to do that.
Beg your pardon?
Elon Musk want to do that.
I don't know what he wants to do. It depends on the day. So we are living in I hear a sea of air. I don't know, thin layer of air. At the top, well, not at the top. At around the 100-kilometer range, we start getting into the ionosphere, right? And we all know what the components of the ionosphere is because you just took your exam. What are the components of the ionosphere? I'll give you a hint, 3. It's okay. DEF, right?
Yeah.
DEF, right? And all you guys that love to do HF love F, right?
F1 and F2.
I beg your pardon?
F1 and F2.
F1 and F2 during the day, F1 at night. We'll get to that. So it refracts HF, right? And then you got the E, and then you got the D. Who likes the D?
Nobody.
Nobody, right? The D can allow for some ducting for VHF and UHF, right? We accidentally will hear some station in Milwaukee, right? How the hell did you get here, right? Ducted. And when I started to do this project, which I guess now is 2 years old, I was totally confused. I could not figure out, A, how the signal got to back to us, and B, more importantly, what's the mechanism here? Because I couldn't grasp, because I'm so used to thinking about the D level as being some evil thing that knocks out long distance AM signals during the day. Okay, we'll come back to that point. All of a sudden, as we go along in this discussion, we're going to find out the D level is pretty important. But let's go back for a minute to our Earth and that thin layer of gas that surrounds it, we call the atmosphere, and the ionosphere. You say, well, like this. Why am I going like this? The ionosphere is different on the day side than the night side. Why is that? Well, it's the sun, right? It's the sun. That's the Earth. This is the sun. Everything's to scale. And we've got 1, 2, 3, 4 levels in the day, right? D, E, F1, F2. And at night, you got what? F. Okay, so what's making these things? The stuff coming from the sun. And by stuff, I mean electrons, protons, but mostly UV and X-ray. Well, what's making it on this side? There's darkness. Darkness is making it. That's the cosmic radiation is making it, right? The cosmic radiation is stuff that's coming out of exploding stars, black holes, just stuff floating around in space. Not floating, and we're talking about energy, but you get the point. Without the ionosphere, by the way, we would be continually bombarded with this stuff, and we'd all be dead. Or more to the point, I guess we wouldn't have evolved because our ancestors would all be dead. Okay. So I've impressed upon you that the Earth has a very thin shield. This thin shield is obviously affected by what the sun feels like. If the sun is happy and moderate and mild, this is all stable, right? If the sun is angry, and by angry I mean is releasing flares and outgassing and maybe firing off a coronal mass ejection or two, all this stuff, the ionosphere gets disturbed. We must work the D, right? Disturbed. Okay. When I initially looked at this whole thing, I couldn't really figure it out. I couldn't wrap my head around this because we love the D, or we love the F, because the F is our friend, because we HF, and we're told the lower the frequency, the more the D will eat your signal, right? Because it'll eat HF and the AM bands. It doesn't eat very low frequencies. By very low frequencies, I'm talking about like 22 kilohertz VLF. As a matter of fact, it behaves almost like the F layer does to HF. It bounces off. And all of a sudden, I'm thinking, oh, okay, I sort of get this now. The signal, the D is not eating VLF signals. It's allowing them to bounce off. Okay? And if it's going to bounce off, technically refract, right? Nothing's really bouncing. Then maybe like an HF signal, we can receive it, which is what an SID monitor does. It receives a signal that's being refracted through from the D layer. So let's talk about, like I've touched on solar weather. Let's talk about very low frequencies. All around the world, governments, in order to help us people who want to measure the ionosphere, have built great big antenna farms with literally antennas kilometers long. They're doing us a favor, aren't they? Or maybe they want to talk to their nuclear attack submarines, which is probably more likely why they'll throw $1 billion into a project like this. These things at around 22 kilohertz can talk into the ocean. The signal is so long that it sucks along the ground and then into the water. And then the sub can pick it up with an antenna that's trailing behind that's a couple of kilometers. Okay? That thing will cover mountaintops. And there's what, 70 in the world. It astounded me. How many people got submarines? That's a little scary. What?
How many antennas do you got?
Roughly 70.
Wow.
Yeah.
So I guess those are work during the daytime, but not during the evening.
No, these are VLF stations. That is a broadcasting station that talks to, can talk to submarines. The signal is so long. Think of it. You know how long the signal is, and it sucks along the ground and then sucks into the water.
But the D will disappear during the evening.
Say again?
The D layer will disappear during the evening.
Yeah, I got nothing. We're not talking about D layer at the moment. We're talking about how they think this thing works, right? They don't care about the D layer. When you're the commander of a military submarine, you're getting your signal from this thing, which is in gigawatts. Like it is pumping out. It's powerful as all hell. The signal comes out of this antenna, travels along the ground, and then sucks into the sea. Okay, D layer has got nothing to do with it at this point. That's what its intended purpose is. That's why they built this thing, so they can talk to their submarines. The Russians had one that covered 4 mountain ranges. Now, we get we get a scattering of this. And this is what confused me because these long waves they're not like sky waves. They don't bounce off the HF, but there's enough leakage, enough just going randomly that we can see them. Okay. We can see the signal. We see the signal by magnetic loop. You all know that we tend to draw electromagnetic signals as sine waves, right? And we tend to think of them as electrical waves, but it's an electromagnetic wave, an EM wave. And orthogonal at 90 degrees to your electrical component is your magnetic component. And you can build an antenna quite easily that can measure the magnetic component of radio waves. So this depends on a magnetic antenna to measure to get a signal off of these gigantic broadcasting systems. And the broadcasting systems, when they send most of their power down over here and into the water, some of it leaks up here and hits the D level. So let's go back and talk to the D level. The D level is, why do we have the D level? Because of the sun. What is the sun putting there to make the D level? X-rays and UV. X-rays and UV. So let me ask you a question. If the sun is angry and it's sending out more X-rays and UV, what happens to the D level? Say again? Thicker. And if the sun is not constant, the D level will constantly be changing, right? Thicker, thin, it's very disturbed. And that's really what we're measuring. We're measuring the disturbance off the D level being bombarded from the sun. Now, there's a constant flow of energy from the sun. Okay, that's why we have every day we have the ionosphere every day, and when it's nice and quiet, as I said, ionosphere, each of these levels is kind of stable. They don't go up and down. They don't thicken and thin. They stay where they're supposed to be, and it's nice and quiet. There are things called coronal mass ejections. Do you guys know what that is?
Blast of plasma off the sun.
Blast of, billions of tons of material, right? The sun is one gigantic magnetic ball. It has more magnetic fields and even more poles than Carter's got pills. And these lines of magnetic force start looping. And if they break, this field can disappear, taking with it tons and tons of matter. Now, when I just say that the D level, for example, is composed of X-rays and ultraviolet, that's not matter, that's energy. And that's like 8 minutes, right? The speed of light, it takes 8 minutes for light to come from the sun to the earth. So in 8 minutes, that UV and X-ray is hitting us. A CME is composed of particles and X-rays. Well, actually, it's not composed of X-rays because while X-rays might be released at the time that the CME is created, they're moving ahead at the speed of light. The protons and the electrons are moving at some incredibly high speed, but significantly short of the speed of light. It can take anywhere from 18 hours, as it did in the Carrington event, to weeks before a CME will hit us. CMEs are very dangerous. If you were in a spacecraft, you could be barbecued. If you were a spacecraft or a satellite, you'd be barbecued. If you're on the surface of the moon or the surface of Mars and you got hit, you'd be barbecued, right? Because you would have no protection against this enormous amount of energy. Flares are slightly different. A flare is because you're dealing mostly with energy, not with matter. So there's very little matter involved with a flare. And again, the magnetic field of the sun snaps and releases a pile of energy. Why do they call it flares? Because you're an astronomer, you're looking at the sun, you'll see it flare. it will actually make a mark on the sun that you can see, right? And that energy can come sliding toward us, and it can wipe out satellites. What did Musk lost 100 satellites in an afternoon because of flare? You know, the massive amount of radiation hit it. So what protects us? The ionosphere, right? But the ionosphere may not always be able to protect us. If you have an enormous amount of energy, it can overcome the ability of the ionosphere to buffer that energy. In 1859, there's something called the Carrington event. You guys familiar with it?
Wasn't around then.
I thought you'd always been around. It'll have to be. Carrington event, antennas, telegraph wires served as antennas. And there was so much energy pouring in from the sun that teletypes, keys were working all by themselves. Operators were getting shocked when they touched their equipment, because what you have is a network of antennas, right, across the country called telegraph wires. This puppy probably caused, 1 million cases of cancer. I'm making up a number. I don't know what the actual number is, because it bombarded Earth with massive amounts of energy in high energy fields. Now, if we had a Carrington event today, you see the movie Eli? Yeah, I mean, they say, oh, the CME caused it, right? I don't know whether the CME would cause craters. I don't think so. But what it would do is knock out our civilization completely. All our nice radios would be fried. Like it's an AMF on steroids. Okay. Drop. Now, do I have your attention? We can all die. Now, what does this thing do? What is this thing I'm talking about? The device.
Measure the atmosphere.
Say again?
Measure the atmosphere.
Well, it's going to measure the disturbance in the D layer, and it's going to give you data showing what that disturbance is, and that disturbance is telling you what the sun's doing, right? Remember we said if and you said it gets thicker when it gets bombarded, so you will be able to figure out how much energy is flowing from the sun by studying that disturbance. The actual device is really quite simple. You have a magnetic loop antenna. I deliberately draw it like that because that's how we tend to build them. There's one up here. If you go up above this metal roof, you'll find one. The unit used to be in there before I took it to the lake. And it goes to an amp, which goes to an analog, the sound card in your computer, which of course goes to software. I think I did that. This, by the way, the antenna, while it's quite easy to build, it's a pain in the butt. I was using house wire, THHN, which is because I was doing surface wiring in the cottage, and I could not make it work with the solid. I had to use the multi-strand because otherwise it was just way harder to work. So, and in my particular case, the bigger one is out in Kenora. It's 4 feet by 4 feet by 4 feet by 4 feet, and it's 500. It started as 500 feet, a coil of THHN, which it's electrical wiring. It's what you use to wire your house, non-Romex stuff. Romex is when you got the 3 conductors in a nice plastic sleeve, right? This is each conductor is independent, and it's if you want to use a channel to wire. So 500 feet, which is over 2.5 times the size of the antenna here, and I'll show you what the signals look like in a minute. But I want to tell an amusing story first. I had extra coils of the solid core, but I couldn't make that work. So I used my only coil of THHN green, which is ground color, for this antenna. And then I went into town and found I couldn't buy any in Kenora. I'd have to go to Winnipeg to get more. So it originally started at 500, but I had to take some out so I could finish wiring my cottage. So now it's 420. And I forgot to buy some today. So when I go back tomorrow to finish the wiring, it's going to be down to about 350 because I need some more ground. So VLF, low frequency, 22 kilohertz. Around that, there's a range because each antenna, of course, is broadcasting a slightly different frequency. VLF and D are friends, which took my brain quite a few months to figure this out because I always viewed D as like, get thee behind me, Satan. Okay. There are many different kinds of flares. I've only described it as you got a CME, which is the large mass of actual protons and electrons and mass coming at you. We talked about flares. Flares come in different flavors. You got A, B, C, D, E. I got it backwards. These are the and then you get the CME. A, B, and C, you won't notice on Earth. It's just all about differences in energy levels, right? These go up in energy as we slide down that scale. The C, D, and E, well, C won't really see on Earth. The D and E is where you're getting an effect on Earth. By the time you're hitting E, you're losing all your radio communication, right? The aurora is spread out to 3/4 of the way toward the equator, and you're disrupting the ionosphere. Is so disrupted, you're not bouncing anything off of it. It's not going to refract anything. It's too excited. Then the device, the equipment that we can get our hands on or build, will measure C through CME. But it's not sensitive enough for A and B. And when I say we can build it, there's the Stanford Solar Center in Palo Alto, California, produce a kit. See, so this is something I built from scratch. It's a kit. They give you, if you're a school, you can actually get it for nothing. But I wasn't a school, so I had to pay a little money for it. So you get a kit and all the instructions. An idiot's guide to making an SID device. Stanford, the software, by the way, is linked to Stanford. So when you build your SID device to measure the ionosphere, your data goes to Stanford, where it's accumulated, then given to NASA. And by accumulated, I mean there's hundreds of stations across North America. You can go on one of their sites and you'll find us. Now, I haven't put anything on there for about a year because I took it away, but there's WSC with a registration number. The second site, the one that's in Kenora, will also be WSC2 and a registration number. So that we are making a citizen science contribution in terms of studying the ionosphere. Okay, what do you actually see?
Void, whiteboard.
What's that? Well, I'm going to show what the data looks like when you do it, right? So you got a signal, you got intensity over time. This is night. This is night. Which makes this what? Day. And day is when the sun comes out, right? That's definition. At night, you're just simply getting some cosmic ray. It's very nice and stable, usually. You better hope it is. If there's a supernova within, can't remember, a couple of light years, we will be wiped out by it. But that will disturb at night. And during the day, you have that sort of as a baseline. Those that have actually seen the output of our machine knows ours doesn't quite look like that, but we'll get to that in a second. You get a flare during the day, and it looks like that. There's a trailing edge. And today, if the system was set up, you would get a kind of a mess. With each one of these could be individual flares or chunks of individual flares. And of course, then you've got an intensity measure. And you can tell there used to be, I had some examples posted on the bulletin board, but they disappeared a while ago. I should have brought them. They're sitting in a file cabinet in Kenora. And you can do all kinds of calculations to make projections on this is a measurement of a aspect of solar weather. And what that is showing you the disturbance in the D. The VLF signal bounces off, comes back, it attenuates, then it goes away. It's very noisy. It can be very noisy. So you have two different. Your data comes at you, of course, instantaneously, right? But you want a 24-hour, or at least a period of time to study. 24 hours of the 12 hours during the day you want to study. So the software will take each one of these slices, and then they add them all up and average it out. Our actual data on an instantaneous basis looks like this, with this being about 20 kilohertz. I thought, and those that were in that room, when they saw the instantaneous data, would say, what the hell is that? First, I thought this was a artifact of the lighting or some interference from our computers or whatever. But it's the same in Kenora, which is pretty electrically silent. I'm off grid. Like all the power I make is coming off of solar panels and batteries. So I don't know why ours looks like that when I'm told it's supposed to look like that. But when you accumulate it and average it all out, it ends up looking like that on a daily basis. So if anybody's got a theory as to why I have a raised noise level from, say, 10 kilohertz to 20 kilohertz, they can let me know, because I don't know what it is.
Closer to the pole.
Say again?
Closer to the pole.
Closer to the pole.
To the North Pole.
Where,
Magnetic fields coming into the North Pole, does it make any difference to that? Like if you took your antenna and moved it 400 miles north, would it change that?
I don't know.
Or
Is
north
that
south?
what
I don't know. I don't think so.
Does
But
that only happen once when you
No.
set up the device?
no, it's constant. First I thought it was the computer. I changed computers. I was using my laptop. Now I'm using. I borrowed one of the WSC's mini HP, and then I thought it was, well, maybe it's fluorescence or some background here. But if it's happening in a cabin that's sitting in the middle of, hundreds of miles from the nearest real electrical source, so that ain't it.
Reference from our solver.
Say again?
have reference from another location? Is this happening to the south or?
It happened here and it happened in Kenora. That's
Yeah, but we are more or less at the same distance.
that is absolutely true. More or less the same. I think that's the same question that
Going down south.
you know what? I don't know. There are so few of these monitors in Canada that
Are you able to see the data from the States? They
yeah, the
absolutely-
states are flat.
Oh.
Yeah. But I haven't really looked at it. I mean, you got a good point. I haven't looked at it as the Canadian data, right? I didn't think of looking at that. So, I mean, this is obviously US centric, right? Because most of the stations, individual science stations are in the United States. It's run by Stanford, right? Out of Palo Alto, NASA project, funded by NASA. Now, I'm going to stop here for a moment. Do you have any questions? Yes, sir.
That data is public and I can access it from the website or somewhere or just is like computer here.
I'll post the website. If you look under Stanford, yeah, they'll menu driven and you can get to it. Stanford Solar Center. You won't find us because we're now a year old. Our data is a year old, and I haven't reconnected. But you'll find everybody else's data, right? Like.
But then you say the disturbance was here in Canada. I mean, between this latitude, latitude, right? The disturbance that you see is between Winnipeg and Kenora, right? So we have the same
profile.
Same profiles.
Same. This is your instantaneous baseline.
And that data in particular is not in that website yet.
No. Our stuff is not there because it used to be there. But it's not there because when my ability to get on the internet in an off grid is through my phone as a hotspot. So I didn't bother. I have to figure out next year how I'm going to set up an internet site in my 20 by 20 foot workshop. What?
You want to do Starlink?
Say again?
You want to do Starlink? Starlink.
Starlink. We'll see. We'll see what I use, right? But I'll have to do something. Go ahead.
But that data can be shared in the website, the RAM website?
No,
No?
not on our RAM website, no.
Or USB, SOC to.
No, I mean, the data was being sent when the system was here. They were sending that data to Stanford every day.
Okay.
And then it got sent from there to NASA. Because he's off grid right now, there's no internet connection, so we're not sending it anywhere.
Okay, so you just saw that and that's it. You saw the disturbance and in the graphic or whatever you're seeing.
Go
That's
ahead.
it. Like you're talking about you saw a disturbance,
Yeah.
right? Here in Winnipeg and there in Kenora.
Sure.
Right? And that data in particular from those observations is locally handled or used a snapshot of the graphic and that's it.
This is, excuse me. You have different windows you can pick.
Okay.
Okay. There's a 24-hour window, right? It's going to average your signal over 24 hours, right? And then it sends it to Stanford. Or you can take another window, right? And manually say, well, I want to look at 6 hours. I want to look at 5 hours. This is instantaneous. This is,
You saw
1 second, right? It's finite. It's not, can't remember how many seconds. It's a few seconds. Yeah. Yeah. I mean, something like this is a 24-hour. Okay. Now, here is, let's go back here. This is an instantaneous one. You'll see peaks on it. Say, pick a quiet time. These peaks are these VLF stations. Those big ones that talk to submarines. Okay. The magnetic antenna is just, and what you do to you find the station that you want to follow. or a number of stations. You can actually follow up to 6 stations and integrate the signals from 6 stations. We're doing 3. Initially, I did 6 and I couldn't, nothing happened. Like, I think it was just too much information. If we settled on 3, there's actually a big station in North Dakota, but we can't read that one. It's too close. Like, we're measuring Hawaii, Maine, and somewhere else. Excuse me, I have to consult my notes. All right, it's Oahu, which is Cutler, Maine, and Washington. Not the capital, the state. Now, you can actually get this data, crunch it, and create solar weather predictions. Yeah, you can get solar weather predictions. I haven't got that far yet. I've crunched the data, but I get distracted by doing things like wiring the cottage and, trying to figure out why this is looking like this instead of a flat baseline. I mean, it's exciting when you get a disturbance and you can go like there are satellites up in orbit. You can access their data and compare it to yours, right? If you get nothing and they're getting something, you're not doing something right, right? We will always, we'll find if them up in space is reading it, we'll likely read it. But again, we're reading not the lowest of the flares. We're reading the getting up there, right? Because the antenna, it's a magnetic loop antenna. It's only 4 feet. And so we're not as efficient as it could be. And I don't have enough wire to make a 20 by 20 or something like that. And a pain in the ass of making one. So part of the background of this whole project is that we have a number of radio astronomy projects that are underway. Those who were here before would have remembered the hydrogen telescope, right? Built a telescope for Jupiter and Io. Jupiter is one of the most dangerous places to be in the solar system. It has a huge magnetic field. Io runs through it, releases from its volcano sulfur dioxide, which interacts with the magnetic field, gives off a signal in the 20 meter range. And we had an antenna set up at my brother's. You need a lot of square footage for a couple of dipoles, right? And we worked out how to get them the dipoles to talk to each other, right? Reinforce each other's signal. And my brother, there's another amazing story. He says to me, "We gonna kill the birds?" I says, I'm listening, I'm not broadcasting. I says, but if I start broadcasting, it's because I'm on my way to get my Nobel Prize, because we're talking aliens now, right? So and when I get back from my hidey hole in Kenora, be spending a lot of time here, and we'll be continuing to work on these kinds of projects. So Sunday was traditionally the day in which we worked on these things, but we hear more often. So,
Are you gonna fit a VLF antenna into your yard?
a VLF antenna. This is an antenna that is not that big.
Only 4 feet.
4 feet by 4 feet, right? That's not that big, and it doesn't really matter. You don't need like height. You don't have takeoff angles and all of those neat things you need to optimize HF signals. You have it's just a low efficiency antenna that'll measure magnetic. Now,
Because those transmitters are really, really powerful.
they're very powerful, and your antenna can be aimed, right?
So Chuck, the antenna, are you wrapping, you said you had a couple 100 feet of wire, are you wrapping the
500.
wire around?
Yeah.
Yeah.
Okay,
Think
so
of an
4
AM
feet diameter.
Think of an AM broadcast antenna in your transistor radio, just wound around.
Yeah.
Right, same sort of thing. 500 feet.
And is there a space between each coil?
I'm trying. I'm trying, right? You know, that's why the thing ends up being, you know,
10 feet thick, but
yeah. You don't wrap it around each other, you know. And as I said, I thought I was going to be able to do a solid wire and have lots of extra wire for the project, but I can't. Like I can't. You can't. I couldn't get it to wind. Like it all fell off and just a mechanical problem. But I was going to say something about aiming. You all know magnetic antenna, right? Where the null is, right? The null is coming out this way, right? Orthogonal to the open. Like the signal is being received this way, right? Onto the external of your wiring or whatever you're going to use for your magnetic antenna. So you do have to pay some attention to which way it's pointing, because if you put your null toward your signal source, well, you might get nothing, right? Of course, since it's bouncing around a bit, you still might receive, but you got to play with it a little bit. You have to play with it a little bit. So sort of an answer to your question, the only real measure or only real mechanical thing that you need is something to allow you to pivot the antenna.
But you could transmit it as well.
If you had a transmitter in the VLF range.
Well,
Because we're licensed for that too.
we're licensed for down there. I don't know if we're licensed. I doubt if we're licensed on any of the frequencies that nuclear submarines use. I have a feeling there would have been an objection. I went through the 60 meter stuff. You know, we tried to get 60 meters and got 5. You know, it was the military that objected because they had some stations and signals on 60 meters. So if I can't believe that we would be able.
Yeah, there's some bad law for amateurs.
Hmm?
There's bad
In the
law.
600 meter range,
Yeah. But
Yeah.
I don't know.
I'll watch it on YouTube.
What's that?
I'll watch the rest on YouTube.
Okay.
Pretty cool.
Well, I mean, any one of these items you can spend hours on, but it's get 8:30. There is a source that all those that might be interested in radio astronomy. It's SARA, Society of Amateur Radio Astronomers. And if you look at the demographics of who's member, about 60-70% of them are hams. The rest of them are engineers and university professors. That seems to be the demographics there. And SARA is only one organization dealing with amateur radio astronomy, right? And they're big proponents of this and many other projects, you know, that are related to radio astronomy. Technically, this is not radio astronomy. You're dealing with, you know, measuring atmospheric events. Now, the D layer, by the way, is at the edge of space. It's 90 kilometers up, generally speaking, with the E and the F being actually in outer space. Are there any questions? Yes, sir.
I was curious, what precipitated you to get into this field of study?
Well, I was always interested in astronomy. And the neat thing about this is you don't have to go out when it's 40 below. You can be inside, right? That sounds strange. So you got a guy who likes radio and a guy who likes astronomy, right?
And
What does that suggest?
What do you use for software? You see it driving the thing.
Well, it's just basically what do they call it? There's Stanford has developed a software package that you'll get, and it runs on Windows. It's their choice. But
Open API to access. There is like open API to access that data or not at all. Like you can build your own stuff.
It's an open API.
yeah, you can. I mean, there's nothing technologically speaking, other than the software. There's nothing really complicated about this. I mean, you've got a mechanical, you know, easy to make antenna. I mean, there's some tricks to it and pain in the ass, but I mean, it's not. Yeah, you can build it. You got a low amplifier. You can buy low noise amplifiers almost all over the place, right? And you need an A to D converter, right? Which is your sound card on a computer, and then you need the software because you need to change those nice little bumps and that into something that you can do measurements of.
It's just like signal processor in the computer. You can do a signal processor with MATLAB or something like that to grab from the sound card, right? It's something like that. It's a signal processor or mathematical the signal processor. That's it, or is much more on that software because you can do some advanced analysis of sound using MATLAB in order to go more deeply into that. So I suspect if you just grab sound, you can put that into that piece of software, MATLAB, with the waveform, whatever tools that there is in there, and you can do your own analyzing tool.
I bet you can. I can't.
My understanding is that because the frequency is low enough, you're able to pick up the sample from the sound card directly. You don't need any other kind of receivers like SDR. You don't need actual hardware. You can just connect the
Yeah, you
sound
don't
card.
need the signal processor. That's it.
Yeah. That's a very good point because
The frequency is low enough to use the sound card directly.
you're not having
This sounds like FTA.
Yeah.
yeah, go ahead.
So there is a magnetic disturbance between Africa and Brazil over the Atlantic Ocean. Magnetic disturbance meaning as in the magnetic field is low in that area.
Yeah,
And
okay.
any satellites flying through that area are susceptible, in particular, to CMEs and the protection of magnetosphere, which goes up more than 100,000 kilometers of the ionosphere.
I know what you're talking
Way
about.
up.
Yeah, I know what you're talking about.
So that sort of helps protect us from the radiation coming towards us too, as well as the ionosphere, and the little thin atmosphere protects us as well. So that little anomaly is a problem for CMEs coming in. So they'll come in greater through that hole, so to speak.
Yes,
Lower magnetic area, which is what led me to asking you the question about the North Pole, which also is low magnetic sphere, is that the magnetic fields all come down towards Earth at the two poles.
Mhm.
So straight off magnetic pole,
You get more cosmic energy, more solar
cosmic
energy
energy.
at the poles.
which then led me to believe, like, okay, we're farther north now, so our magnetic sphere is closer to the Earth
Yeah.
at the equator, for instance.
So we just see if we are able to have the station Dolphin or even further away, Blingflow concept.
Yeah, so I'm wondering if that's what sort of causing your differences in your up straight line and your curve line, because we have less magnetic sphere over top of us than somebody in Stanford or down in the southern states or at the equator, other than the whole.
No, I understand what you're saying.
Yeah.
And I can't answer that question, right? I don't know.
We
Right?
need data, like having the solution being built in Dolphin,
Well,
Blingflow
should-
concept.
Your data would be if you took that to Texas one day and tried it there.
well, and then one day Flin Flon. Yeah. Flin Flon in February. No, I've done that. We're gonna pass, okay? Hard pass. Well, I got a very nice coat though, from there. There is a way to have an actual look at the data, which came up in the conversation, which is it's in Sanford. I do not have a comprehensive list, although I can get one, of all the Canadian stations, right? Like you could just go look at the Canadian stations, right? The other Canadian stations, like they welcomed us because their data is they don't have a lot of data points, right? And Winnipeg, I don't think there were any data points. Certainly nothing in Kenora, right? I mean, I can't even buy wire in Kenora. So, I mean, that would be something that you've given me a something to look at, right? Because maybe there's somebody in Churchill. Like if you were a university or something, you'd probably want to see if you could set a station up just for fun.
Because the thing that you're saying, it's true, we get points of south to north. We probably will see the gradient changing.
Maybe.
Yeah.
When you look at the magnetosphere and its shape, other than the Van Allen belt and the solar flares actually push the magnetosphere out, right?
Yes, they do.
So when you're facing the sun, your magnetosphere is closer to Earth, and on the other side, it's trailing outwards, which could be what affects this D layer at night. I don't know. We have barely passed reactance and resistance, so.
So, you know, and it's a simple project to put together, but it has layers to it. I mean, you know, like, where's that book? I mean, they publish a book like this to tell you how to do all the analysis for your space weather. But I haven't come across this particular drawing anywhere in here. And when I asked the question, they didn't seem to know what the answer was. I don't know, it's supposed to be flat. Well, it ain't, and it's in 2 locations, right? One location, you know, well, okay, it's environmental interference from fluorescent lights or you know whatever. But but now it's different computer, different location. You know, there is not much different antenna. Yeah,
But they're all your property.
say again.
But they are all your property. Those 2 locations are all your property. That's the same.
It's you.
It's me. Good point. It is me. I walk up to it and it decides to do this.
Pacemaker is blasting signals.
Yeah.
Anybody else have questions, Jeff?
Yeah, so the other question is, on your hardware itself for the antenna, what's the spec on the wire you have to use for that antenna?
Well, it's quite forgiving. I'm happening to use 14 gauge, you know, AWG, right? THHN, which is thermoplastic, high temperature, high heat.
Why
No,
14? So
because that's what was in the roll that was right there on the floor, right?
You
Like,
can do it
you can do it with any.
anywhere you want.
Yeah.
24 gauge, like
Yes, and you can do it on thin, like the one upstairs is. I mean, I must be half the gauge of the 14. And why I keep pointing down there is it's you know where the hell am I going to get the wire? I went down to I went to my supplies, right, and cannibalized it.
They
So-
don't use the enamel coated stuff, like when you're making an AM antenna for transistor radios. Those are the same thing. As long as they're not touching to each other, the wire's not touching.
you can get some really thin enamel coated wire pretty cheap.
Oh, there's no question. I did not pick the cheapest route. I picked the one that it's right here. Yeah. And then I had to cannibalize it because okay, I'm going to put another circuit in. I need some more ground wire. Right. So, and I'm going to put another circuit into this week. So I'm going to be cannibalizing it some more if I forget to go to Home Depot and pick up another roll of 14 gauge wire. You don't happen to have any, do you? Just kidding.
Stranded.
Hmm?
Not stranded.
Yeah. Well, stranded was an accident because I couldn't the only green was stranded, and I thought I could do white, and black. Now, wouldn't that confuse me? You know, a year from now when I couldn't remember what the hell I had done.
Interesting. Okay, wait. Thank you, Jeff.
Hmm? This one?
They
Off and on for about 2 years.
Unity.
Yeah, but like
I
not
remember.
continually. Like when I went to last year when I went to Texas, I put together finished off the hydrogen radio telescope, which I already did a lecture on. And